Hey y'all, it's Sarah. Today we're continuing the calculus series, the applications of differentiation portion with derivatives and the shapes of graphs. So the first thing we're going to talk about is a function being increasing or decreasing on certain intervals. So it looks like over here our function is decreasing and over here our function is increasing, right? But let's figure out if there's a way that we can actually tell that just from the function itself without graphing it. And it turns out there is. It's called the increasing/decreasing test. So basically, the derivative of the function x squared is going to be 2x. So I'm going to go ahead and draw in that line. So this is f prime equals 2x, right? And so you'll notice that where f of x is decreasing, f prime of x is negative, and where f of x is increasing, f prime of x is positive. And this is actually a rule called the increasing-decreasing test. Basically, this is always true. If the derivative of a function is positive on a certain interval, then the function is increasing on that interval, and if the derivative is negative on an interval, then the function is going to be decreasing on that interval. Now, it turns out that increasing and decreasing isn't the only thing that we can tell. There's also something called the first derivative test, which is a way to tell where our function has local maxima and local minima. So basically, for this test, we take the critical points of a continuous function, right? Function must be continuous, and we consider any critical point c. If the derivative is changing from positive to negative at c, then f has a local maximum at c. Now, let's think about how this looks, right? If f prime of x is changing from positive to negative, the function itself is going from increasing to decreasing, according to the increasing-decreasing test, right? And so it makes sense that at the top of that hump, we'd have a local maximum. The same is going to be true for a local minimum. If at a certain point c, our derivative is changing from negative to positive, the function's changing from decreasing to increasing, so we have a local minimum. And then if f prime doesn't change sign at c, so say it goes like this, then there's not going to be a local maximum or minimum at c. So this would be a graph of f, right? And we see that its slope is staying positive the whole time, so there's no local maximum or minimum there. So let's look at some examples here. So we're given this graph, and the first thing that we want to do is, well, we have to identify that it's continuous. It is. And then identify the critical points. So that's the places where the slope is 0. Clearly, that's going to happen here, here, and here. And now we want to see, from the graph, we can see that we're going to have a local minimum here and a local maximum here and nothing here. But let's actually consider what's going on at those points, right? So as we approach this first point from the left, we're decreasing, right? F prime is going to be negative. And then here, we're increasing. Our slope is positive. So based on the first derivative test, we wouldn't have to have the graph to know that this is a local minimum. And then for the middle point, we go from f prime being positive to, okay, we're still increasing. F prime is still positive. So this point is not a maximum or a minimum. So we have a minimum, we have nothing. And then for our last point, we go from f prime being positive to, okay, f is decreasing, which means f prime is negative. So by the first derivative test, we're going to have a maximum here. All right, let's try another example. We're looking at the graph of sine, right? And we want to figure out where it has maxima and minima. And so the way that we're going to do that using the first derivative test is to look at the graph of its derivative, which is cosine, right? So the first thing is we need to identify the critical numbers, the critical points. Those are the points where the derivative is 0, so where cosine is 0. So that's here, 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 and then they're an infinite number, right? They go on forever. These ones are as well, but we're just going to look at the ones that are fully on our graph. So we've identified those critical points. So let's see what's happening at, okay, negative 3 pi over 2 here. That looks like the slope's 0, so this makes sense. Negative pi over 2, same thing. And then at pi over 2, also looks like the slope's 0 there, and at 3 pi over 2. Okay, now in order to tell if these points are maxima or minima, I mean, it's obvious visually, but we want to do it just based off of using the derivative, which is cosine. So we want to see the changes that cosine is making from positive to negative and from negative to positive. So at negative 3 pi over 2, we're changing from positive to negative, which means that sine is going to have a maximum there. At negative pi over 2, we're changing from negative to positive, so sine is going to have a minimum there, a local minimum. At pi over 2, we're changing from positive to negative, so this is going to be a maximum. And then at 3 pi over 2, we're changing from negative to positive, so sine is going to have a minimum. So even if we didn't know what the graph of the original function looked like, if we knew what the zeros of the derivative were and whether it was positive or negative in between those zeros, then we could always tell where the maxima and minima of the original function are. The next thing we're going to talk about is concavity. So basically, concavity is this idea of, so it's concave upward on an interval if its graph lies above all of its tangents, and concave downward if the graph lies below all of its tangents. So let's get some intuition on this by just drawing some tangent lines. So at this point, the tangent line looks like this, right? If we made it longer, we'd see that it's above the graph, right? Here, tangent line, that's a bad drawing, but something like that. Here, like that, here, like that. All the tangent lines here are above the graph, right? The graph lies below all of its tangent lines. So here, we're concave downward. And it kind of makes sense when you think about the idea of what concavity means in real life, right? It's basically like the bend. It's bending down. Now, we have a point here where suddenly things change and it looks like we're bending up, right? If you draw the tangent lines to some of these points, you see that the graph lies above these tangent lines. And so here we're going to be concave up. Now we have another point where things change. Around here, our tangent lines start to be above the graph, right? Our graph is below its tangents. So it's concave down again. And then around here, it changes again. And so this is concave up. Now, there's a name for these points where things change. They are called inflection points. So a point on the curve where the concavity, so if the function is continuous there and the curve changes concavity at that point, then it's called an inflection point. So all of these blue points are going to be inflection points. Now there's a way to test for concavity. That's going to use the second derivative, all right? So if the second derivative is positive on an interval, then the function is concave upward on that interval. And if the second derivative is negative, then the function is concave downward. So we're going to look at this in practice using sine. So since the derivative of sine is cosine and the derivative of cosine is negative sine is going to be our second derivative. All right, so we want to figure out where the second derivative is positive and where the second derivative is negative. First of all, let's identify our inflection points. So those are going to be places where f double prime is equal to 0, right? Where it changes between negative and positive. All right, it's positive here, negative here, positive here, negative here, positive here, and negative here. So although this is pretty clear on the graph of sine already, we can use the graph of its second derivative, negative sine, to figure this out. So These are our points of inflection because they're the zeros of the second derivative. And because we have a plus sign over here, right, the second derivative is positive, we're concave up over here. From negative 2 pi to negative pi, the second derivative is negative, so we're going to be concave down, which makes sense when you look at the shape of it, right? And then negative pi to negative pi over 2, second derivative is positive, so we're concave up. Then second derivative's negative, so we're concave down. Second derivative's positive, so we're concave up. And then at the end, second derivative is negative, so we're concave down. So that's how we figure out concavity. And the concavity changes between these, so like it's concave down between those two inflection points, and then concave up between these two inflection points, and so on. At an inflection point, there is no concavity, right? That's a point of change. Sort of like how when you have the derivative being 0, it's not increasing or decreasing at that point. Similarly, at a point of inflection, we are not going to actually have concavity at that exact point. It just determines a change in concavity around it. All right. Now, the second derivative also gives us another useful way to figure out where we have local maxima and minima. So basically, what we had done before with the first derivative test was figure out where f prime was changing from, right, positive to negative. So the function's going from increasing to decreasing. And that means we have a local maximum. But you'll notice, looking at this, that this is also concave down, right? The same goes for when the first derivative goes from decreasing to increasing. So we're going from, it goes from negative to positive. So the original function goes from decreasing to increasing. We have a local minimum. And this looks like it's concave up. So the second derivative test, we're assuming that the second derivative of our function is continuous near some point x equals c, right? So if f prime of c equals 0, meaning if f prime of c, right, like if we have a critical point there, if we have a critical point there based on the first derivative, and if the second derivative is positive, so critical point and second derivative is positive means we're concave up, that is going to be a minimum. And if it's a critical point based on the first derivative, and if the second derivative is negative, we're concave down based on the concavity test, so f has a local maximum there, right? Let's see this in practice. So now I drew out sine x, that's our first function. The first derivative of it is cosine, and then the second derivative of it is negative sine. So let's use our second derivative test to figure out where the maxima and minima of sine are going to be in this domain. So the first thing we have to do is see where is f prime of c equal to 0, right? What are our critical points? So we have this point, this point, this point, and this point. You could also include these two, but I'm not going to because it goes on forever and we have to stop somewhere. So those are going to be our critical points. Now we need to see if f double prime is continuous near them. Well, negative sine is continuous everywhere, so that works fine. And now we see where the second derivative is positive and negative. So, at negative 3 pi over 2, our second derivative is negative, which means, based on the second derivative test, that this is going to be a local maximum. At negative pi over 2, which is our next 0, the second derivative is positive, so sine is going to have a minimum there. At pi over 2, second derivative is negative, so we're going to be concave down, meaning we have a local maximum. And then at 3 pi over 2, which is our next 0, f double prime is positive, which means we're concave up, so we have a local minimum. All right, now just to recap what all these tests are for. So if you want to tell whether a function is increasing or decreasing, you only have one option for this in terms of these derivative tests. That's the increasing decreasing test, which requires you to find f prime. And then if you want to find the concavity of a function, use the concavity test. That's going to require f double prime. If you want to find the maxima and minima, you have two different options. The first derivative test, which only requires the first derivative, or the second derivative test, which requires both the first derivative to find those critical points and also the second derivative to figure out, basically it's applying the concavity test to tell you, okay, if we're concave up and it's a critical point, meaning the slope is 0, then that means it must be a local minimum. So lots of different ways to apply both the first and second derivative. All right, if you enjoyed this video, please like and subscribe, and I'll see y'all next time.